Once we have performed the experiment, now it's time for us to plot the graph of photoelectric current I versus voltage V. When we increase the voltage by adjusting the rheostat, more electrons reach the anode. Hence, the current increases. But until at certain voltage, the photoelectric current becomes saturated, and this is labeled as IM. When the voltage then reduced to zero, we can still detect some photoelectrons with sufficient energy that are able to reach the anode, and the current is then labeled as I naught. When the voltage is made negative by switching the negative terminal of the power supply to the anode, the current starts to decrease further until it reaches zero. This 0 point is labeled as Vs, or stopping potential, where the voltage is strong enough to stop any photoelectrons from reaching the anode. Let's take a look at Einstein's photoelectric equation. HF equals to W naught plus Kmax, where HF is the energy of the incident light, W naught is the work function of the metal, and Kmax is the maximum kinetic energy of the photoelectron emitted. Kmax also is the kinetic energy, which is half mv max squared, or EVS. So what is work function? Work function is the minimum amount of energy required to eject an electron from a metal surface. Work function equals to HF naught, or also equals to Hc over lambda. These are a few examples of metals with specific work functions. Maximum kinetic energy Kmax is equals to half mv max squared. Kmax is basically the excess energy left to move the photoelectrons to get ejected after the light is able to overcome the work function of the metal. Thus, the magnitude of Kmax is directly proportional to the frequency of the photons. The higher the frequency, the more Kmax received by the photoelectrons. But Kmax is not affected by the intensity, or you can say the brightness of the light. When we rearrange Einstein photoelectric effect equation, and we know that Kmax is half mv max squared, or equals to EVS, thus we can get that EVS equals to HF minus work function. Threshold frequency F naught is a minimum frequency required to eject the electrons from a metal surface, also known as a cutoff frequency. So threshold frequency depends on the type of metal used. So what is stopping potential Vs? Vs is the minimum value of the negative voltage when there are no photoelectrons reaching the anode. From EVS equals to Kmax, we can say that Vs equals to Kmax over E. E equals to 1.6 times 10 to the power of negative 19 coulomb. So basically, we can say that once we are able to determine the value of a stopping potential, we can determine the magnitude of the kinetic energy held by a photoelectron. There are three critical steps in order for you to determine the stopping potential Vs. Plate C, or you can also call it the anode or the collector, should be connected to negative terminal. This is to retard the motion of the photoelectrons, as we know that photoelectrons is negative charge, so they should oppose each other. Step 2. Vary the voltage until there's no more current detected on the emitter. This shows that the photoelectrons have been stopped from reaching the plate C. And lastly, determine the Vs, or the stopping potential, from the IV graph when you see that the current is at 0. Let's take a look at the variation of photoelectric current with voltage. I have three cases, and let's discuss the first case. Although the photoelectric current can get saturated when light shines on the metal, we can still increase the current by increasing the intensity or brightness of the light. Note that we don't change the frequency, just increase the intensity of the incident light. Here, the the intensity of the photon is doubled. Hence, the photoelectric current is also doubled. Notice that the stopping potential Vs is still the same. Hence, we can see that frequency gives the energy to each photon, but intensity of light is the number of photons that hits the metal surface. So we can say more photons hit the metal, more photoelectrons get ejected. For case 2, when two different lights have the same intensity, we will observe two different stopping potentials with the same photoelectric current intensity. The light with higher frequency has stronger Vs, hence located more to the left. For case 3, when the intensity and the frequency of the light is kept constant, but the two types of metal is used. The metal that has lower work function gives up more kinetic energy to the photoelectrons. Hence, it requires bigger stopping potential to retard the motion. Work function smaller, stopping potential is bigger. Now let's take a look at three various graphs to represent the photoelectric effect experiment. We have three graphs: Kmax versus frequency, current versus intensity, and stopping potential versus frequency. So for the first one, Kmax versus frequency. X-intercept is the threshold frequency of different metals, and the Kmax is directly proportional to the frequency of light. For current versus intensity graph, the gradient of the graph represents the wavelength of the light. The higher the intensity or the brighter the light, the more photoelectric current it produces. And for the last graph, stopping potential versus frequency, X-intercept gives us the value of the threshold frequency. The Y-intercept gives us the value of work function for each electron, and the gradient of the graph is the Planck's constant per electron. Now let's do some exercises. You may pause the video to read the questions. In order to get the threshold wavelength, we have to change the value of work function from eV to joule. From here, we use work function equals to hc over lambda. H is the Planck's constant, c is the speed of light, and then we divide it with 7.23 times 10 to the power of negative 19 joule. And the final answer is 2.75 to the power of negative 7 meters. Question B is asking for Kmax when the lambda is 200 to the power of negative 9 meters. By using Einstein's photoelectric equation, substitute all the values, and for the work function, take it from question A. And finally, we can get 2.72 to the power of negative 19 joule. For question C, we can get the value of the Vs simply from the Kmax. We use the formula Kmax equals to EVS and substitute the Kmax, and charge for one electron is 1.6 to the power of negative 19 coulomb. And your final answer is 1.7 volt. You may pause the video to read the questions. We are given the energy of a photon in electron volt. Hence, we need to convert it into joule first before we can calculate the wavelength. Thus, we get 3.6 to the power of negative 19 joule. From here, we use E equals to hc over lambda, substitute all the constants and value accordingly, and the lambda is 5.525 to the power of negative 7 meters. For question B, the Kmax given is 1.1 electron volt. Again, we need to convert it into joule, and the answer is 1.76 to the power of negative 19 joule. We are going to use Einstein's photoelectric equation to find the work function. You can get the energy of the photon in question A and minus the converted Kmax just now. Thus, the final answer is 1.84 to the power of negative 19 joule. That's all for chapter 9. Thank you.